This is slide number 29 and I am your presenter Asloob Mudassar. Linear system. A simplest optical system consists of a single convex lens for imaging purposes. Now we come to the definition of linear systems because we shall be using linear systems frequently in our analysis in this course. If for different inputs there are different outputs, the system is said to be linear. Look at the diagram. The system consisting of an optical system, for example, you can feed it input 1, you get output 1, then input 2, output 2, and so on. For the nth input you get nth output. So the output is unique to the given input. Such a system is referred to as the linear system. For a coherent illumination, the system is linear in amplitude. If we are using a coherent system, then the inputs will be amplitude, the outputs will be amplitudes. But if we are using incoherent illumination, the input will be intensities and the outputs will be intensities. Now for a coherent illumination, there is a definite phase relationship between different parts of the inputs, whereas in incoherent illumination, such phase relationship does not exist. So for a given input, the different points in the input have a specific phase relationship between them. Such a system is called a coherent system. And if there is no such a relationship, then we say that the system is incoherent. Now we can represent the above system in the following form. That is, capital X is equal to the summation of all the inputs we have fed to the system one by one, and the system has given us an output, and we have on the right hand side the superposition of all the outputs giving you a total output equal to Y. So X is the superposition of all n inputs, input I, and Y is the superposition of all n outputs, that is output I. So X is our total input, Y is our total output. So we can feed to our linear system, we can disintegrate the total output X into n small inputs, and we can feed these inputs to the system, and then we will get corresponding to each input an output I. So we shall get n outputs I, and we can combine them, that is, we can superimpose them to get the total output Y. In Fourier optics, the optical systems which are linear in complex amplitudes will be considered at large. Optical systems which are linear in intensity will also be discussed briefly. So in the Fourier optics, our main emphasis will be on the coherent systems, where we shall deal with the complex amplitudes. Simple inputs mean that the response of the system is well known. So we shall feed those inputs to the system for which the response of the system is known. Such inputs are called simple inputs. A complicated input will be represented as a superposition of simple inputs. For example, in the previous case, this capital X is the complex input, and we can disintegrate them into smaller inputs or the simple inputs. A complicated input will be represented as a superposition of simple inputs, or a complicated input is decomposed into simple inputs. Let's represent a complicated input O at xy as a superposition of the simple inputs using the definition of inverse Fourier transform. So here we give the definition of the inverse Fourier transform, that is, we represent the small object in space, that is O at xy coordinates, as a superposition, because in the integrals are giving us the superpositions of the optical wave, which is capital O at fx fy multiplied by the phase factor e to the power plus iota 2 pi within the bracket fx into x plus fy into y, disintegrated with the coordinates fx and fy. So this O multiplied by this exponential factor is actually, these are actually the plane waves. You see that here we have shown these are actually the plane waves with the amplitudes equal to capital O. or you can say that O, capital O at fx and fy is actually the magnitude of the wave, or you can say that this provides the weighting factor for this wave. So this is a plane wave and these are the magnitudes or the weighting factors and their propagation vectors making an angle alpha. We have also calculated previously that alpha cos alpha is equal to lambda into fx, and here we have alpha is equal to cos inverse lambda into fx and beta is equal to cos inverse lambda into fy. So with each fx and fy you get different values of alpha and beta that gives you the direction of a propagation of the wave. Analysis of optical systems. So if you want to analyze your optical system, what you have to do is that you have to, the step one is that decompose a given complicated input into simple inputs using Fourier integrals. So if your input is complicated, break up into simple inputs. The step 2 is presents simple inputs one by one to the optical system and calculate the individual responses, that is the individual outputs. And the step 3 is that superimpose the individual responses to find the total response of the system. A linear system actually maps a set of input functions to a set of output functions. So this is the definition of our linear system. In another way, if a system of inputs is represented by inputs O at xy with the corresponding system responses by a set of outputs represented by I at P and Q, that is P and Q are the image coordinates and XY are the object coordinates and PQ are the image coordinates, and you can see that I represents one of the outputs or one of the image outputs at the image plane. Then the relationship between the inputs and the outputs is formally given by. So this is the relationship between the input and output through the system, and this relationship says that I, that is the output at the coordinates PQ, which are the image coordinates, is equal to the system operating at the object function, which is at the coordinates x and y. So system will operate on O and it will give you I. O is the input object and I is the output response of the system. So x, y and p, q are the variables at the object plane and the image plane, and S stands for the general optical system. It could be consisting of a single lens or could be consisting of many lenses. So let's break O, that is the object, into two functions, sigma at xy and omega at xy, such that we can write O at xy is equal to A multiplied by sigma at xy plus B into omega at xy, where A and B are complex constants. So now we can feed this value of O over here in this equation. We can put the value of O over here and then we shall calculate the input response. Let's see what it is. So I at P and Q is equal to system operating at this within the curly brackets. We have A into multiplied by sigma at xy plus B into omega at xy, and you know that the system operator being linear can enter into this curly bracket and can operate on the input function, because S is a function of xy, so it will operate on sigma of xy, and on the right hand side it will operate on the W of xy. Due to the linearity of S, it can operate the function inside the curly brackets, because this is the property of the linearity function. Second possibility is to represent O at xy as a superposition of a point sources, because we want to represent O as a superposition of a point sources because the response of the system to the point sources is generally known. Now let's see how we can represent O as a function of the superposition of the point sources. This O at xy is equal to a superposition integral. The two integrals represent the superposition of O at zeta and eta coordinates multiplied by the delta represents the point source, delta of zeta minus x, eta minus y integrated with respect to zeta and eta. So you see that if you use the definition of the delta functions, that is zeta is equal to x and eta is equal to y, you will get the same on the same thing on the right hand side as you have on the input side. So it means that the right hand side and the left hand side both are the same thing. But we can use this equation for some useful results. Then O, which is at zeta and eta, are the weighting factors of the point source, delta of zeta minus x comma eta minus y. So these are the point sources and are the and we can regard them as the elementary functions. Now the system response is given by I at P and Q is equal to S operating on O, which is at x and y. So since we have O over here, we can plug in the value of O over here in the form of integrals, and then we shall compute the response of the system. X and Y and P and Q are the variables at the object plane and the image plane respectively, as we have stated earlier. So now we are going to operate S on the input. So we have I, that is the output at the coordinates P and Q, is equal to the system operator operating on the input given within the curly bracket in terms of the weighting, in terms of the superposition of the point sources, where O at zeta and eta give you the weighting factor of the point source, and the point source is delta of zeta minus x comma eta minus y. So these are the integral steps that S can enter into the integral, because S is a linear function. So S will operate on the variables which are the functions of x and y. So S will operate on delta at the coordinates zeta minus x comma eta minus y. And you know that we are assuming that when this is the response, that is when S operates on the point source, that is the image of the point source is kappa, that we have given in the last step. Kappa at the coordinates P comma Q semicolon zeta comma eta. So actually kappa is a relationship that maps zeta and eta, that maps the information at the coordinate zeta and eta to the coordinates P and Q. So kappa is very important. So this depends upon the function on the system operator S. So S has operated on the point source and it has given you the kappa as the output of the system. So what is the input? Input is the point source, and what is the output? Output is kappa. So you see that this is the if the system response to the point source is known, which is kappa in this case, then of course you can calculate the superposition of this kappa with the weighting factor, which is O at the coordinates zeta and eta, will give you the integrals, will give you the superposition. So the superposition of this quantity on the right hand side will give you the quantity of the input on the left hand side at a single point P and Q. Okay, now due to the linearity of S, it operated in the integrals as we have described earlier. So kappa, which is P comma Q semicolon with zeta eta, is the response of the system to the point source located at P and Q at zeta at x and y in principle on the object plane, and is referred to as the point spread function. So kappa is actually the point spread function. So you know that when we have an object point and we have an image point, the image will be a blur version or the spreaded version of the input. So we call the kappa, because kappa is the response to the input to the input point source. So kappa will be regarded as the point spread function. The function kappa at the coordinates P comma Q semicolon zeta comma eta has a definite functional form. If this functional form retains its functional form when the point source at the object plane undergoes in-plane shifting, then such a system is referred to as the invariant system. So you see that here we are giving the definition of the invariant system. What is the invariant system? Is that the kappa will not change its functional form. So kappa depends upon the two set of coordinates. One is zeta eta, which is related to the input coordinates on the object, and P and Q are related with the image plane coordinates. So if you change zeta and eta, then you have a response at the coordinates P and Q. The kappa will retain its functional form, so kappa will not change. Kappa will change its position when zeta and eta will change, but the functional form of the kappa will stays the same. Such a function in which kappa has fixed functional form, kappa can change its position on the image plane, but the shape of the kappa is fixed. The functional form of the kappa is fixed, such a system is referred to as the invariant linear system. The center of the function kappa at coordinates zeta comma eta semicolon with zeta eta is located at p is equal to zeta, q is equal to eta. So here here at the SH plane we have actually eta. So this is the center of the kappa. And around that center kappa is sitting at that point, that is kappa is sitting at the coordinates p is equal to zeta, q is equal to eta, and of course this will be the center of the kappa function. For an invariant linear system, kappa pq comma zeta eta only changes its position according to the input but retains its functional form. Such if kappa retains its functional form, then we can write kappa, that is the left hand right, can be written as according to the right hand side, that kappa is equal to p minus eta comma q minus eta, which means that kappa has the fixed functional form. So p minus zeta and q minus eta means that the kappa can change its position according to the value of zeta and eta, which are linked with the object point coordinates. So when zeta and eta will change, the kappa will change, because kappa will change its position as p is equal to zeta and q is equal to eta, but the functional of kappa will stays the same. The definition of invariant linear system is that it remains the definition of the linear or the definition of the invariant linear system remains valid only in a small region around the optical axis called the isoplanetic region. So you see that this definition, mathematical definition, that we have given kappa from the left hand side compared with the kappa on the right hand side. The kappa on the right hand side, this definition of the kappa works for the invariant linear system. It means that this definition is applicable only to a small region around the optic axis, which we call as the isoplanetic region or the paraxial region. So we shall be considering kappa as unchanged in its functional form when we are talking when in the isoplanetic region or in the paraxial region. For invariant linear system, the integral takes the form. Then you know that we can write the previous integral, that the response of the system I at the coordinates p and q is equal to integrals indicate the superposition of the object O at the coordinates zeta and eta multiplied by the functional form kappa, which is p minus zeta and q minus eta, and this integration is at the coordinates zeta and eta. We can also recognize, those who are familiar with the mathematical integrals, you know that this integral is actually the convolution integral between the object O and the kappa, which we describe in the next. The integral can be recognized as convolution integral between two functions O and the kappa, and can symbolically be represented as I at the coordinates p and q is equal to O at the coordinates p and q convolved with the kappa at the coordinates p and q. So this O is actually the ideal image at the image plane under paraxial approximation under geometric optics. So O is the image at the coordinates p and q, because p and q are the image coordinates, and you know that O is the same, O at the object is the same at O at the image coordinates p and q. So we can regard O as the geometrical image of the object O convolved with the kappa, because kappa actually the point spread function of the system. So kappa at p and q. So the convolution between O and kappa will give you the output I at the image plane. This states that the convolution between the object field and the system PSF gives the image field. In this course, only the linear invariant isoplanetic optical systems will be discussed. So remember that we shall mostly be discussing the linear system which are invariant and which follow the isoplanetic region. Those systems will be considered. Now here we are specifying the integrals very clearly for the isoplanetic system and for the non-isoplanetic system, that is for the invariant system and for the non-invariant system. So the convolution integral will also can only be written for the invariant system, so you see that this integral is the convolution integral, and this is applicable for linear invariant isopolaritic optical systems. Now look at this integral, which is the second integral. It has kappa, which is not written in the form as given for the previous integral. So kappa, the functional form of the kappa here can change from point to point. If zeta and eta will change, the position of the kappa, which is p and q, which will also change, but the functional form of the kappa will also change. Such a system is referred to as the linear system, but non-invariant system. So mostly we shall be dealing with the those systems which are isopolaritic. That is, we will be dealing with the integral, the first integral, and sometimes when the system is non-linear, we might be dealing with the second integrals. So here, this is the end of slide number 29.